In this problem we have the Hamiltonian of harmonic oscillator, and in part A we're supposed to show that the Hamiltonian can be also written as the following expression: h is equal to h bar omega times a dagger a plus 1/2. And a dagger a are the ladder operators, they're given, and we can just go ahead and plug them into the following formula, and we will see if we come up with the original expression. So because QP don't commute, we have to multiply the mixed terms mixed. So that's just basically QP minus PQ, and that's the commutator, which is given by I h bar. And so when we simplify this, we have I squared, which is minus 1, times h bar over m omega. And when we simplify the brackets, we're going to get h bar omega times, and so we have m omega q squared over 2h plus, I forgot the square here, plus p squared over 2h bar m omega, because the m omegas are going to cancel the square in the denominator. And then we have minus, so we have h bar over omega square m omega, and that's going to cancel the h bar with m omega in front of the brackets, so we just have minus 1/2, and then we have plus 1/2. And the minus and plus 1/2 are going to cancel each other, and we're left with, if we expand those brackets as well, we're going to get m omega squared q squared over 2 plus h bar omega, well, the omega is just going to cancel the other omega, h bar p squared, well, the h bar is also going to get cancelled, so we only have p squared over 2m, and the plus and minus 1/2 is just cancelling each other. So that's the Hamiltonian. And if we compare that to the original expression that we had here, we can see that that's basically the same expression as we have here. And the meaning of a dagger a is just, that's going to give us the end state of the harmonic oscillator, and that's basically just giving us the n operator. So that's the reasoning behind it. So in part B, we're supposed to compute the Hamiltonian with a dagger commutator, and let's just begin by doing that. So Hamiltonian with a dagger commutator, and we can basically use this expression here for the Hamiltonian. I'm just going to copy it. And that's commuting with a dagger. And so if we expand these brackets, we're going to get, I can pull the h bar omega in front, and I have a dagger a in commutator a dagger plus 1/2 a dagger, and that's just 0 because a constant a commutator with a constant is just 0, so that's basically 0. And we can expand these brackets as well. We have, so there's this rule that when we have product commuting with another operator is just A commutator BC plus AC B. So if we use this formula in this expression for the brackets, we're going to get A dagger A dagger plus A dagger times A. And we know that the operators commutes with itself, so that's just going to give us 0 as well. And we know that the commutator A dagger is just 1, so basically the whole expression is h bar omega A dagger. And we also have to show that for an eigenstate n of h with eigenvalue En, the state A dagger n is also an eigenstate of h. So when we have h working on an eigenstate n, that's just going to give us the energy eigenvalue of n, and we need to show that that's also an eigenstate. So if I rewrite this, I have A dagger of n, and I can use a little trick that's going to allow me to simplify this problem. A dagger h minus A dagger h, because I just added and subtracted the same expression, so I basically changed nothing, but that allows me to simplify the problem with the commutator, which is this, and that's just the commutator h bar A, h A dagger, and then I have this expression left, and that's just the eigenvalue En. And so we know that this is also h bar omega A dagger. And then I can just rewrite this as h bar omega plus En times A dagger of the eigenstate n. So that's what we needed to show. So now in part C, we have a given relation, which is A working on a state 0, and it's giving us 0. So we need to find the position representation of the ground state wave function, phi 0, which is given as the scalar product of Q times the 0 state. And we need to find an expression as well for the first excited state, which is phi 1. And we're giving this hint that we don't have to calculate the normalization constants, which is going to simplify the problem, basically. So let's just begin by seeing what we know by now. We have the operator A working on 0, the 0th state, and that's giving us 0. So we want to find the position expression of the wave function, which is phi 0. And we're doing that by basically projecting the position vector onto this state. And we know that this is 0 because that's given in the problem, so that's just the operator of phi 0 is just 1. And we know that the operator is given as such. I can just copy this. And I'm gonna basically multiply that with phi 0, just because I want to find that. So we know that the momentum operator is given by minus I times h bar times the first derivative, and I'm just going to plug this into the expression above. So we're going to get m omega over h. Well, I can just leave that out because the whole thing is basically equal to 0, so it doesn't even matter. So I have q times phi 0, and then I have negative I times I, which is just plus 1, and then the other constants that are left times the first derivative, and that's just the first order differential equation that's separable, and I'm gonna simplify it. So now that we separated the variables, I can just integrate both sides, and that's going to give me ln of phi is equal to, that's just a basic integral, m omega q squared over 2h bar, and plus a constant. So in order to find phi, I'll just take the exponential basis, which is just going to give me phi 0 is equal to exponential. So I'm raising basically both expressions to an exponential, and that's just another constant a. And so that's the ground state wave function, which is not normalized, of course, but that's not even asked in the problem. So now we have to find the first excited state, which is basically just the projection of q onto the first state, and we know that the ladder operators are raising or lowering the states, so we can use the trick that we know that the raising operator is just going to raise the 0th state, and we already know what the wave function in the ground state looks like, so we can just use the raising operator of phi 0, and that's just going to give us what the first excited state looks like. So I'm just going to copy that again. And we already know what phi 0 looks like. And I can plug in for operator p again. The operator q is just q, and then I'm going to get minus I squared, which is basically just plus, times h. So I have h over m omega times the first derivative of the function, and the function is a e to the negative m omega q over 2h. And so when I take the first, q squared, yeah. So when I take the first derivative of this expression, it's just going to give me 2q m omega over 2h times the e function again, and the 2's are going to cancel, and of course the constant a is just going to stay in the front, and so I basically have q m omega over h bar, which is going to cancel with this h bar m omega, and I'm going to be left with just q a, and there's another q here, so that's just 2 times q a, of course. And then the e expression. And so that's basically what the first excited state looks like.